Welcome everyone. I'm Jonathan Bartlett and I'm doing an introduction to Scheme programming. How many people here have done Scheme before at all? 2. Wow. So this is a little shocking for the Tulsa Lambda lunch. Lambda actually largely comes from Scheme. So that's kind of what there's a lot of languages after it that use Lambda a lot, but Scheme programming was the one that really made it popular. So we're going to be talking about Scheme and what makes it great. Okay. Now, a quick note about me. A lot of you don't know who I am. I'm the chief nerd in charge at New Media. I also do a lot of other stuff. I'm the director of a nonprofit called the Blythe Institute. I'm the owner of a very small publishing and teaching company called BP Learning. I'm the leader of Tulsa Open Source Hardware. We meet the third Wednesday of every month at New Media. If any of you like Arduinos or anything like that. I'm the author and editor of a bunch of books. You can see some of them there. 2 in particular that you all might, or 3 in particular you all might be interested in is New Programmers Start Here. So if you know anyone who's getting into programming and doesn't know where to start, that's the goal of the book. Building scalable web applications using the cloud. That was actually, there's a lot of Techlahoma people who helped me out on testing that one out. So if you want to know about building scalable apps, you know, the ins and outs of doing that, that's a great book. Programming from the Ground Up is assembly language on Linux. So it's kind of an old classic. It's been around since 2004, but it still sells copies because it's probably one of the few books on the topic. I'm also an educator for classical conversations. I do a lot of I teach homeschool co-ops. I teach a variety of classes. I'm co-pastor of Reunion Family Church, and I'm also a husband and dad. So as you can tell, I get bored really easily. So super short, kind of, you know, just to give you a bird's eye view of Scheme. This is a Scheme program to do a factorial function. Are you all familiar with factorials? Factorial 5 is 5 times 4 times 3 times 2 times 1. Okay, so this is a very, this is how you would write that in Scheme. So notice everything has parentheses. So you start out, so actually if we start in the inside, you never have order of operation problems in Scheme because everything is dictated by the parentheses. Okay, so Lambda creates a function, and so in Scheme, functions and definitions are separate. Okay, so they have syntax that combines them, but you should always think about the function itself and the name of a function as separate things. So Lambda defines a function, creates a function that has a parameter x. So that's what that Lambda x does. And then above it, you see define factorial that gives that function the name factorial. So it separates out building functions and naming them. Okay, and then within the function, we say if x is less than 1, then return 1. Otherwise, multiply x by the factorial of x minus 1. Okay, and the operation always comes first. There are no primitive math operations that it does special syntax for. It all has the same form, right? So multiply is the function, minus is the function, factorial is the function. They all operate the same way. Okay, so that's just so you have a feel for what it looks like. At the end, you can say factorial 5. And it'll return 120, which is 5 times 4 times 3 times 2 times 1. All right? Does that make basic sense? Can you kind of see how that works in general? All right. So why Scheme is a great language? Okay. So Scheme winds up being one of the perfect languages to testing out new ideas in programming styles and programming languages. Scheme actually attempts to remove as much syntax from the language as possible. That's why if we go back to that, there's almost no syntax ideas. You've got your literals, you've got your bare atoms, the words and the numbers. You've got parentheses, and that's pretty much it. There's no special syntax. There's no special keys that do anything special. It all is the same basic syntax. So it basically removes syntax and just gives you a parse tree. You're typing in a parse tree of your language. Okay. Scheme attempts to actually remove everything as much as possible. It's a minimalistic programming language. They try to give you a very small number of tools, but a very small number of very powerful tools. Okay? Scheme also attempts to equivocate between code and data, right? Because a lot of times, a lot of languages today have reflection. That didn't used to be something that every language had, but now, today, most languages have it. But reflection usually is pretty hard to mess with. They all have lots of custom functions, custom data structures. A lot of work goes into doing reflection. In Scheme, code and data are the same structure. They're all just lists of items. By doing that, it makes it real easy to write programs that manipulate other programs and programs that generate other programs. So Scheme tries to put just a few tools in your hands, but make sure that they're the most powerful tools possible. In fact, a lot of the modern programming practices and ideas come from Scheme. And to give you an idea for just how minimalist Scheme is, I've put out a graph. This is a page count of language specification. Okay? So the C++ specification has 525 pages. So Java is at 700 pages. Now these do not include the libraries, right? This is just the language itself, right? How the syntax works. Scheme comes in at under 50 pages. Now, but also that page count for Scheme includes its standard library. So it's 50 pages for the language definition and the library versus the next closest contender is C, which is at 175 pages. And that's just the language. So as you can see, it really is a minimalistic language. You can learn the entire language, top to bottom, in about an hour. Now, so Scheme actually came from Lisp. If you've known any Lisp, you probably recognized, hey, that Scheme looks a lot like Lisp. And a lot of people make fun of Lisp, saying there's lots of irritating, stupid parentheses. Right? Very, very valid complaint. It's one of the oldest languages. I think there were only one or two languages before Lisp. And I don't know how many of you are familiar with the history of computer science and theoretical computer science, but there's basically two models for programming. One is Turing machines, which is what we're used to thinking about computers in. That's where you basically have a processor and it pulls in memory, operates on it, pushes it back. There's another model called the lambda calculus. And Turing machines and lambda calculus both do the same things, but they're conceptually very different. Lambda calculus is about functions, passing functions, and manipulating functions. And there's not a difference in what you could do with these two ideas between manipulating bits and manipulating functions, but there's a difference in how you think about things and how you implement them. So Scheme actually originated as a tiny Lisp interpreter. It was a group that was, they were trying to test out some ideas in programming languages. They're like, hey, we need let's start with a small Lisp. And so they built a small Lisp, and it just kind of evolved from there. It developed through a series of papers from MIT's Artificial Intelligence Lab, for things such as developing cheaper mechanisms for function calls in compilers, simplified mechanisms for complex control flow, and just rethinking the way that compilers and languages and people work together. So a lot of people think of Scheme as a functional programming language. Technically, it's not. A functional programming language doesn't really allow assignments. Usually in a functional programming language, you try to avoid assignments to variables at pretty much all costs. Scheme actually, most Scheme programmers make a kind of hit the boundary where it's discouraged but not forbidden. And then the Scheme standard is based on, it's called RNRS, which is a revised report of the Scheme language, and the N is the revision number. So R5RS is kind of the standard Scheme that most people know. There was an R6RS that everybody hated, and now they're working on R7RS. So this talk is mostly based on R5RS, which is pretty old, but it's pretty standard. So what a lot of people don't know is that JavaScript actually borrowed a lot of scheme ideas because Brendan Eich, the developer of JavaScript, actually originally planned on putting Scheme as the programming language for the browser. That was his original idea. That was actually technically what he was hired for. He was hired by Netscape to build Scheme into the browser, but because Netscape contracted with Java, they wanted a language that looked more like Java. So he modified what he was thinking about to make it look more like Java, and JavaScript was the result. So there's a lot of things that are in Scheme that are also in JavaScript because that's really what Brendan Eich wanted to do anyway. So, and that's where JavaScript borrowed them from. So why should anyone learn Scheme? Well, first of all, I'm a book guy, and some of the best computer science books are based on the Scheme programming language. How to Design Programs. I mean, How to Design Programs is a super intro book, but nonetheless, it's one of those books that really make you think twice about how you design programs. Structure and Interpretation of Computer Programs is a standard text from MIT that just goes really deep into thinking about development from a functional programming standpoint. Programming Languages, an interpreter-based approach, is a really good programming languages book if you want to know just general information about programming languages. They use Scheme because there's so little syntax in Scheme. And we'll show other reasons why Scheme is great for programming language development. There's also the Little Schemer and the Season Schemer, which tells you a bunch of tricks that come out of Scheme. But the most important reason to learn Scheme is that it will change your imagination. I mean, really, I like to do things that expand the way that I think about things. Your imagination is your biggest tool, and so doing things that expand your imagination on how code is put together will always help you. It makes you think differently on the relationship between code and data. It makes you think differently on, why do we have syntax? What's it for? How does it work in a program? It helps you to think about how to pare features down to a minimal set, and how to make things powerful without making them cluttered. Okay. It'll also help you understand modern programming languages better because a lot of ideas are borrowed from Scheme, and people will just refer to them, and they might refer to them by name and not tell you about them, and just assume that the people listening know something about Scheme and understand what they're talking about. Okay, so Scheme syntax. The goal of Scheme syntax is to have as little of it as possible. Okay, so procedure call. You have the procedure name, and you have your argument list. Argument lists are separated by spaces. There's no commas. I mean, there are commas, but they actually are part of identifiers, I think. Can't remember exactly what commas do. So procedure name, arguments, put the whole thing in parentheses. Okay, the first element is the procedure, and it's technically not even procedure name. It's the procedure is the first thing. It might be an identifier that refers to a procedure, or it could be a lambda itself that defines a procedure and then runs the arguments on it. Names can have dashes. That does not mean procedure minus name. It's because if it meant the minus operation, the minus would be the procedure and it'd be in front and there'd be a space. Okay. So most things in Scheme are procedure calls, even arithmetic. Right. So here it's organized as procedure calls. So it does plus 1 and 9 to give 10, minus 5, 3 gives 2, and multiply both those together and gives you 10. Okay. So it goes inner to outer just like most function calls anywhere else. The if statement, so the basic if statement, you have if, then you have a condition check procedure. If that condition check is true, it runs the then procedure, and if it's false, it runs the else procedure. Okay, so here's an example. If x is less than 3, so notice less than is a procedure. It's not an infix, it's actually a procedure call. Less than x3 means if x, so that means it's going to run less than procedure with arguments x and 3. And that procedure returns true if x is less than 3 and false if it doesn't. So if true, it displays I am a small number. If false, it displays I am a big number. All right. Any questions so far? Does it make sense? Everybody following? All right. Basic syntax, lists of values. Everything is in Scheme is a list, including the code, right? When you're doing code, you do those procedure calls. What it's doing is it's building a list internally and then running them. So everything in Scheme is a list. Now, if you want it to be interpreted as a literal list instead of code, you just put a quote mark in front of it. Okay, that's known as quoting. And so if I do quote and then I do 1, 2, 3, it'll return me the list 1, 2, 3. If I didn't have a quote, it would try to interpret the 1 as a procedure. And then it would give me an error. It says 1 isn't a procedure, right? Here, that returns the list A, B, B, C, C, where it uses, so here, those are called symbols in Scheme. You can think of them as actual identifiers. They don't refer to anything. They're just symbols. And so they are just as much as part of data as anything else. As I said, code and data are essentially the same thing in Scheme. And the third one has a number, then a symbol, then the string hello. Okay? So lists can contain lists. That's a list within lists within lists. You can also quote individual values. So if I hit A, that would evaluate A according to its current value in the present context. So if I had assigned A to 5, that would return 5. But if I do quote A, that returns the symbol A. Okay. So here are some basic list operations. So here I define X to be that list, the list 1, 2, 3. The function car returns the first element of the list. Now the reason for these names actually go back to the names of the machine instructions that the original Lisp was built on. So that's why they have funny names. So car, I believe it stands for contents of address register. And CDR stands for contents of decrement register. So that's why they have funny names. But car means the first element of the list. CDR means the rest of the list except the first element. Okay? So car returns a single item 1. CDR returns a list of the rest of the elements. So even if there's one left, it will still be a list of one element. Then you can use cons to construct a list from individual values. And so notice at the end, so this is how you construct the list 1, 2, 3 manually. Notice it in the last constructor has a empty list at the end. And so that's how you get an empty list. You get a list by adding stuff to an empty list. Okay. So then you get local variables using there's a whole set of let commands, and we don't have time to go into what the difference is between all of them. The most common one is let star. And so basically with let, you notice you have the wide parentheses, and that's your list of variables, and then after that is the list of things that you are doing with those variables. Okay, so that's how you introduce local variables in Scheme. Once it let exits, those variables go away. So there's also a regular let and there's let rec, but as I said, that's too much for what we're doing today. And then there's creating a function, lambda, right? The keyword lambda creates a function. You have the lambda, then you have a list of parameters, and then you have your function body. That can be as many statements as you want. And then the last expression, anytime you have a statement, whether it's a let or a lambda that has several statements, the last statement, the value of that last statement is the value of the whole expression. So your return value is what will be whatever the result of your last evaluated expression is. So lambda functions are born anonymous, but they can be given names with let, set, or define. So set is how if you need to change the value of a local variable, you can use set. So here is an example of a function from doubling. So it basically gives a value x and doubles it. So lambda x means create a function with a parameter x, multiply x by 2. Now we're going to take that function, give it a name, double me. Now when I say double me 23, that means pass 23 to my lambda function. There's the same thing using a let. There I define double me as a local variable, and I set it to, it's the same function, and it's the same binding. It's just this is a local binding rather than a global binding. Does that make sense? Everyone following? All right. So a couple miscellaneous things. Booleans are £t and £f. Quote open close parens is the empty list. Functions that yield side effects are usually marked with a bang, not always. For example, set modifies a variable. Semicolons are used for comments. And I left a blank bullet just for fun. All right, so recursion. Scheme really wants you to use recursion. Okay, so most procedures can be written either procedurally, which is like with while loops or each loops or something like that, or they can be written recursively. Okay, so if you're thinking about procedural routines, you're usually thinking about the method of how something is done. When you think about things recursively, you're usually thinking about the logic of how something is done. And so Scheme really wants you to focus on the logic and make everything recursive. So even when you have a while loop, Scheme wants you to make that into a recursive loop. So basically, your recursive function, and so in case you didn't know, recursion means the function calls itself. And we'll see an example in a second. Usually write code that does three things. Check to see if you're done. Perform a single task well, and narrow a bigger task to a smaller task. All right. And so this is actually very similar to how you do inductive proofs in mathematics. In fact, this is doing it this way will actually allow you to make your programs provably correct. If you encapsulate this process into a recursive program, you can eliminate a lot of variable problems that show up in while loops. Because a lot of times with while loops, there'll be variables that you forgot to modify, things like that. And by doing it as a recursive program, you have to explicitly pass each variable back into the process. So because that you have to be explicit, it makes you think about each variable and what it's going to be the next cycle around. So here's an example. The top one is a procedural program for eating 100 apples. And this is simplistic and just to make it easier to look at. So int apple index equals 0. While the index is less than 100, we're going to eat the apple with the index. Apple index equals apple index plus 1. So you can see it's very procedural. Do this, do this, do this, do this. Okay? So this is a recursive program for eating 100 apples. Okay, so what we're going to do is we're going to define a function with our loop. So eat apples will be the loop, and it'll be a function that takes both the index and the number of apples. Okay, and so and what we're going to do is first we're going to check with an if statement to see if we're at the end. If we're at the end, we're not going to do anything. We're just going to return false. Otherwise, we're going to do our action. We're going to eat a single apple at the apple index, and then we're going to call eat apples again with new values. Okay, so this procedure, rather than the while loop does a bunch of things, this procedure does one thing. It eats one apple and then moves you to the next one. Okay, and then we kick everything off by calling it with our initial values. So they do the same thing. These two do the same thing. The difference is that in our recursive loop, we're explicitly marking all of the things that go from one iteration to another. And this isn't very advantageous in a simple example, but in more complex code, it actually becomes super helpful because it avoids any problems of what happens if I forget. It makes you think explicitly about each variable and how it's affected iteration to iteration. Okay? Now a lot of people think, well, recursion is super expensive. You're going to have a stack a mile long, right? But recursion in Scheme is not expensive. Scheme actually originated what's known as tail call elimination. And what that means is that if you have a function, every time you make a function call, it makes a new stack frame, which has the return address and your local variables. You call another function, it adds another thing to the stack. You call another one, it adds another thing to the stack. Okay? Well, if you look on this function, the last thing we do is make a function call. Okay? Well, if the last thing you do is to make a function call, after the function call, you don't need your stack frame anymore. So what in a properly tail recursive language, what they do is at the last function call, they throw away your stack frame and replace it with the next one. So this actually, rather than making a huge stack, is actually a constant stack size, because because we have the recursive call at the very end in tail position, it will actually replace our stack frame each time rather than nesting deeper and deeper. Okay, so basically inside the compiler, it replaces your last function call. Instead of doing a real function call, it'll do a variable rename with a goto, and that will and that makes it super fast. And so by doing this, it eliminates many distinctions between writing elegant code and writing optimized code. Okay? And so here's various languages with tail call optimization, and some of this is dependent on the actual implementation, a lot of other factors. I was surprised C# doesn't support tail calls, because they do a lot of other things really well. F# does. It's supported in the language runtime, but not in C#. Scheme, Scala, Lua kind of does. JavaScript doesn't, which I was also surprised about, being that Brendan Eich was originally going to write Scheme, so I was kind of surprised at that. They added it to ES6, but no one's implemented it, except I think Safari has, but Chrome doesn't even have plans to. So I think Objective-C generally does. It's not part of the language specification, but several compilers do. Python doesn't. Java doesn't. So anyway, a lot of different options on there. The one problem with tail calls is that it makes debugging large stack frames harder, because it eliminates the several stack frames. All right, so I also did an article on IBM on recursive programming, if anyone's interested. So that's recursion. So next we're going to talk about closures. Okay, closures. A lot of languages these days have been coming out with closures. A lot of people are still, I find newer programmers are still a little unsure about them, and even some older programmers who've been mostly doing C-ish languages. Closures allow for functions that generate functions. Basically, so we've shown that in Scheme, function creation is different than giving a name to the function. So if I do lambda, that creates the function, and then I do a define, and that names the function. Okay, well, because I can do a function creation anywhere, wherever it is that you define your function, Scheme uses the variables that are active at the time. You can use those in your function. And then you can, because you can create it, you can also return the function from a function. Okay, so functions you can pass around just like any other type of value in Scheme. So essentially, when you create a function, it creates it with the pointer to the stack frame that was currently active at the time of creation. So here's a little example. This will make a counter. Okay, so I have my outer function, which will be make-counter, and it will be given a starting number. Okay, so then I'm going to create a new function, and I'm going to temporarily call it next value. That name won't stay around very long, but next value will increase my starting number and then return the new starting number. Okay, so I have a function that was defined within a function. Okay, so what happens is that so then at the end of the let, what I do is I actually return that newly created function. So if you go down here, you have define myCounter make-counter 10. So what I'll do is run the function make-counter, give it a parameter of 10. All right, so 10 will be starting number. Okay, so 10 is starting number, and then it creates a new function, next value. Okay, so next value now has a reference to the stack frame, because we created it within the scope, and so it's going to have access to starting number. Okay, so it has access to the current stack frame that was active when it was created. So then it's going to return that newly created function. So my counter now has the next value function that was created when I ran make counter. Okay, So then I do make other counter that runs make counter with a different value. So that creates a new stack frame with a new value for starting number, creates a new function, so that it's the same code for the function, but it's attached to a different stack frame. And then I can manipulate starting number within there. I return that function. So my counter has the next value function from the first call, and my other counter has the next value function for the second call. Okay, so now when I call my counter, I'll get 11. If I call my other counter, I'll get 101, because each of them are going back to that function in the middle, and it's reactivating the stack frame that was active at the time and running the function. So it's reactivating that data. My counter, my other counter, my other counter, my counter. So it goes back and forth depending on which function you're actually calling. Okay, so that's how closures work. And interestingly, for anyone who's done object-oriented languages, objects are basically just advanced closures. Okay, so here is kind of written in a more object-oriented style. Basically, what I'm doing is I'm now creating two functions, one with a next value that does the same thing as before, and another one called reset value that will now change the number to the number that we started with. Okay, so I had to introduce a new variable called original value that saved the value of the starting number. And so now I have two functions, and I'm just going to return a list. It's basically like a hash, associating the symbol next with the function that gives you the next value, and the symbol reset with the function that does the reset. And I can use this. I don't expect you to know all these little things, a lot of schemish things, but I hope you can see that we can call next, 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 reset, next on our little function. Okay, so we're basically emulating objects using closures because they're the same thing. In an object, you have your object data structure that gets activated every time you call the object function. And in closures, you have the active stack frame that gets activated every time you call a function. So they operate very similarly, if not identically. Okay? So that's closures. It's the ability to create functions that get tied to the stack frame that was active at the time. So macros. Macros are another amazing thing about Scheme that allows you to extend the language. And by extend the language, I don't mean make the exclamation point do something different, or but when we talk about the language, because Scheme has so little syntax, when we refer to syntax, we mean like special things that you do with parentheses. Okay, so here there's a customized syntax for let, which means that the first set of parentheses will tell me what my variables are. Okay, so that's the syntax. It's not evaluating those, because normally parentheses mean procedure call, and we're basically saying we're gonna use the parentheses to mean something else on a let for the first part. Okay, so so macros allow us to do rewrites like this. So Scheme allows extension being via macros. Now, if you've used macros in other languages, you might be like, oh, we don't want to use macros. Those are awful, right? Because in most languages, macros are what's known as unhygienic, which means that the macros themselves can kind of clobber your code in weird ways. So if you've ever used C macros, you know that you have to put like 5 sets of parentheses around your macros to make sure it evaluates right. Because if you had a macro that took 2 arguments and your first argument was x plus 5, it might do something with order of operations if you didn't put enough parentheses around it. But in Scheme, macros are hygienic, which means that they work like you imagine they should. They work as if they were a natural part of the language. Let's see here. Unfortunately, macros can't really be used for things like type safety, but they can be used for anything that's kind of allows you to do new things. And macros allow specialized domain-specific languages to be built. Now the actual syntax for doing macros is kind of complex, so I'm not going to go into it here, but I want to give you an example. So we talked about how closures are very similar to objects. Okay, so let's just pretend that I wanted to add, so scheme by itself, bare scheme, does not have any concept of an object. But let's just say that I wanted to add it. Okay, so here is, let's say that I wanted to do this. So I wanted to be able to define a class like this. So I just say class and give the name of a class. And then I give attributes for the class and then give a set of methods for the class. Right? That's very object-oriented-ish. Feels like an object-oriented language if I were able to do that. Now this isn't in standard scheme, but this is what I might want it to do. Okay, then on the right, this is how I might use it. I define a variable, and the counter would instantiate it, and then I would call the functions with next, next. I do set value, set skip, next, next, and so on and so forth. So that would give me my counters in a very object-oriented manner. Okay. The nice thing about Scheme is that if I want to have a language that looks like this, I can. That is the entirety of what it takes to convert that into to make this work as a class definition. As I said, there's no classes in Scheme, there's no objects in Scheme, but if I wanted to add it so I could write something like this, this is the only code I would need. Okay, that's what, 15 lines, something like that. So basically define syntax means I'm defining a syntax called class. I'm defining a couple keywords called attribute and method. Here's how they're formatted, and here's what they do. And so basically I show it how to construct the vtable from my methods, how to associate the names, and I'm done. Object-oriented scheme from regular scheme in about 15 lines. So anyway, so Scheme is basically a build-your-own programming language. As I said, it gives you just a few tools, but they're all very powerful. So because Scheme doesn't have a real syntax, it's just list of lists. You are basically writing, so if you imagine the way that a compiler works, first it goes and it scans your document for all the tokens and creates a parse tree out of those tokens. And what Scheme does is Scheme basically eliminates the first step and it says, you know what, just write the parse tree. And then it takes the parse tree and says, you know what, why don't you just give me a set of macros and I'll interpret the parse tree however you want me to. Okay, so anyway, so if you add parse trees, you add your own macros, and then you add a set of helper functions, you have the ability to build any language. And in fact, people have done this. So this is Racket, is an implementation of Scheme. And basically what you can do with it is you can say, you know what, I want to use some other language. And they have parsers built in that will basically parse, or not, yeah, they'll basically convert the language you want to write into a parse tree, and then they have macros that will convert that parse tree into Scheme. And so here I am in a Scheme system writing Python. And so this is just straight up Python. I did a class called myClass. It's all space-based. And this is all this goes through Scheme, but it works just like Python. And so basically as I said, with Scheme, you can build your own programming languages out of the little pieces that it adds. Scheme gives you lots of options. If you want to compile it, you can use Chicken Scheme. I found that, like with my little class example, I tried it with Ruby, I tried it with C++. Chicken Scheme was twice as fast as Ruby. C++ was twice as fast as Chicken Scheme. So then there's Guile, and if you want to easily add an extension language to your own program, Guile is meant to do that. Racket has a great GUI for development. Chibi, if you need something ultra small, I think like it's like 100K or something like that. And then if you don't like the parentheses, there's a thing called Wisp that allows you to write Scheme code in a more, I should say, Python-ish way. They get rid of all the parentheses and you use indentation instead of parentheses. It's the exact same syntax, it just they found ways of eliminating parentheses. So in summary, Scheme is very minimalistic, but is very powerful. Focuses on recursion and allows you to do that with tail call elimination to keep that from causing you to have your stacks blow up. It uses closures for encapsulation, and that's kind of your universal encapsulation. You don't have separate objects and whatnot. It's just all done in closures. Code and data are treated equivalently, and there's a coherent macro system for language customizations. And so you have a few powerful parts and tools and ways to put them together in unique ways. Any questions? Yes? Yes. It will, in a sense, there's, I mean, I think the actual implementation is implementation specific, but yes, generally they use garbage collection. There's no explicit allocation or deallocation. In fact, even Chicken Scheme, I believe, uses garbage collection. And in fact, what Chicken Scheme does to kind of go midway between having stack frames and eliminating them with tail call elimination is what they'll do is that they garbage collect their stack frames. And so basically, with Chicken Scheme, you actually, even with tail calls, it generates stack frames, but if nothing's referencing them, then they'll be eliminated. And so that way you can actually still use them in debugging, because if your debugger still is keeping track of them, they're still there. But if your debugger's not keeping track of them, they'll be garbage collected. So it's actually a pretty cool implementation. Other questions? So I hope you take some time to go and look at Scheme. I'll actually tell you what I originally proposed doing was that there's actually a different feature of Scheme which I wanted to present on called continuations. And continuations are this amazing Swiss Army knife for flow control. But the problem is that just talking about continuations would take the entire time. And so since you all hadn't done a talk on Scheme before, it seemed like it would be a bad idea to talk about continuations when no one knows what Scheme is. So, but with continuations, just to give you an idea of what's possible, you can use this one method call to generalize the idea of coroutines, exception handling. Even you can do, there's a program you can do where you do ambiguous values. So you can set a variable to be one of a set of possibilities. And then later on, even in completely different code, you just assert truth values. And your code will re-execute until it finds one of your values that satisfy whatever axioms you've put in later on. And so you can do all sorts of magic flow control. It basically makes it work like Prolog. You can put in all sorts of magic flow control with this one tool called call with current continuation. So anyway, but just all of the tools of Scheme are all like that. They're like, oh wow, I didn't know I could do all of that with this one tool. So the tools that they picked are all tools that are powerful. They're all recombinable, and you can use macros to make any system you want. So, all right. Well, thank you all very much.